In a hypothesis test, we ultimately make the decision to either reject the null hypothesis or fail to reject the null hypothesis. Test statistics and critical values can be used to make that decision. So the test statistic is a value used in making a decision about a null hypothesis. It's found by converting the sample statistic, either your p-hat from your sample, your x over n, the number of successes you found out of your number of trials, or your x-bar, your sample mean. You convert that to a score, such as a z-score or a t-score, with the assumption that the null hypothesis is true. And recall, we use the z for the proportion, and z for the mean when sigma is known, and t for the mean when sigma is unknown. And there are other criteria also that we have to consider. Okay, so we will assume the null hypothesis is true and calculate this test statistic. The test statistic for the proportion is this formula. So for the proportion, we said it's z. So we take our sample statistic p-hat, subtract our p from our null hypothesis, divided by the square root of pq over n. Okay, that's how we compute the test statistic for the proportion. For the mean, we have two different calculations depending on whether or not sigma is known. If sigma is known, it's a z-score. Okay, x bar minus mu over the standard deviation. And if sigma is unknown, it's the t calculation, x bar minus mu over s over the square root of n. Oh, let me fix this one. Of course, sigma over the square root of n, the standard deviation there for our sample, distribution of sample means. So we'll get to that as we talk about the critical value. That's a z-score or t-score on the borderline separating the z-scores or t-scores that are likely to occur from those that are unlikely. We've talked about this before, the definition of a critical value. So we could then, let's see, move this up here. So here's an example. A survey was conducted that found 60% of college students had a credit card. So a researcher claims that most college students have a credit card. So to claim most, you're saying that the proportion of college students who have a credit card is greater than 0.5, greater than 50%. That's how we would indicate most. Because anything, if it's equal to 50%, then that's half. And anything less than that would not be most. Okay? So we say we want to test this claim at a significance level. We'll be talking about this in a bit, but we've already talked a little bit about an alpha in our confidence limits, but in our confidence interval construction. But we want to test this claim at a 5% significance level. So we'll say our significance level alpha equals 0.05. So we know our HO will be the proportion is 0.5, but now this is our original claim, right? So the competing claim is less than or equal to, well, that would go with HO, so our alternate hypothesis is this, that the proportion is greater than 0.5. So in this case, our original claim is the same as our alternate hypothesis. That's not always true. Okay, let's look at the test statistic. So our p hat, recall, the problem said, is 0.60, 60%. So our test statistic says we take p hat, 0.6 or 0.60, minus the p that comes from our null hypothesis, divided by the square root of p times q, which will also be 0.5, over n. And in this case, I didn't mention it, but somewhere up here we were supposed to have seen a sample size of 200. Okay, a survey conducted, let's say, of 200 students. And that'll fix that. Okay. So this calculation leads to a test statistic of 2.83. I've rounded to 2 decimal places there. So we said we can use test statistics and critical values to help us make a decision of whether we reject the null hypothesis or we fail to reject the null hypothesis. So let's think about what this would look like. Our normal curve, our z distribution here, where we have a z of 0, and we have calculated a test statistic that's out here somewhere at 2.83. Well, how do we get our critical value to compare to that? Well, that comes from the significance level. So with the significance level, and we're just interested in this upper end of the values here, greater than 0.5. This is where p is equal to 0.5. We're interested in way up here. Okay, so that area that's cut off here from the critical value is 0.05, and I can find the z-score associated with that using my TI 8384 calculator and the inverse norm function. I type in area to the left, if you remember. So in this case, the area to the left here would be 1 minus 0.05 or 0.95, and I get a critical value of 1.645. We did this before in confidence interval estimates. So this is 1.645. Okay. So remember, critical values are on the border separating the z-scores that are likely to occur, all of these, from those that are unlikely to occur, the ones up at the upper level here. And so the z-score we calculated is in the unlikely to occur region, or what we call the critical region. This is the critical region, the area that the critical value borders off here. So if we assume, and here's where we're making our assumption, that p is 0.5, we put it in the place for p in our test statistic calculation. P was here, p is right here. We're putting our assumption that it's 0.5, then this is the test statistic we get. It falls in our critical region, in the unlikely to occur. So this would help us make, or lead us to the decision that we would reject the null hypothesis, because with this 0.5 assumption, this z-score is in the unlikely to occur region, or the critical region.